Hello. Today we will further dive into the statistical basics and discuss the concepts of distribution, sampling, and we will introduce a theorem called central limit theorem. First of all, let's review the concepts of distribution, frequency, and population. First of all, if you remember the previous lecture, we talked about the Galton board. Galton board is a toy, and if you roll many marbles through this toy, you will end up with the situation where you find different numbers of marbles in the bins below. The bins are shown with red squares here. If you watch the video about the Galton board, the physical Galton board, you'll understand what this corresponds to. And if we say, after doing this experiment, after rolling many marbles through the Galton board, and of course we discuss why this type of situation you end up with. Why do you have more marbles in the middle bins but less marbles on the peripheral bins? We've discussed about the reason for this and how to compute the number of marbles you expect in any particular bin. I'm not going to elaborate on that any further, but if we say you end up with this situation shown in the picture, and let's say that you put a number on each marble, the number of the bin is fallen into. For example, if a marble falls into the bin number 5, you write the number 5 on that particular marble, and you do the same for all the marbles. So you end up with a group of marbles with some numbers on it. You will have many 5s, many 4s or 6, and so on and so forth. And if you count the number of marbles with the label 5, or when you count the number of marbles with label 6, for example, and you put these numbers on a graph, you have, say, 10 marbles with the label 5, you have 8 marbles with label 4, or you have 7 marbles with label 6, so on and so forth. This number called frequency of that bin, and the frequencies for the all bins is called the distribution, and the whole set of marbles constitute the population. So let's give an example. For example, you want to know, you're interested in the number of glassware in each household in a country, the country X. For some reason you're interested in this. And this is the distribution of number of glassware in each household. So you can see that the frequency of number of glassware is in millions, because this is the whole country. This is the real population. Every household is included in this graph. Of course, this is impossible to obtain if you don't spend enormous amount of money or an enormous amount of labor. It's a very difficult data to gather, and also it's not something stable. Glassware in a household constantly changes because glass breaks and you buy new stuff and things like that. So it's not something you measure once and stays the same. So this is a theoretical distribution for us. Actually, it exists, but we cannot know about it for sure. But let's assume that for a certain period of time, this is the real distribution. So the number of households with 10 glassware is the most frequent ones. The frequency of those of that bin is the highest, and the other number of glassware, the frequency for other number of glassware per household bins is as shown. And this is a distribution, and this is the distribution of the real population, the whole population. And it's as an average, and in the average is shown by the red dotted line, which is 10. Okay. So, however, you want to know or get some idea about this distribution. What is it? You don't know it, but you know it exists. But you want to get information about this, but you do not have the ability or the finances or the time to go to each household and ask for the number of glassware. What you can do to get some information, you can do some sampling. Sampling means you go and pick up random households and go ask them. Instead of going all the households, you go a subgroup of households. You put on the record the number of glassware in those households. Try to estimate the number of glassware in the country and the average of glassware in a household. The number you're trying to estimate here is 10. We know that because we created this situation. However, the person who's trying to find out what the average number is does not have the information. So he or she samples. And here you 13 households this person visits and gets these numbers. He or she averages these numbers and find an average of 8.5 fish. Of course, as you do an average, now the average number can be anything. It doesn't have to be an integer. The number of glassware has to be an integer, but the average number does not have to be an integer number, as you can easily see. So he or she finds the number to be 8.5 from this 13 household sample. Of course, this has to be a random sampling. If you go and pick the households living in the same neighborhood, in the same city, in the same apartment, these 13 households, you may not be able to get a good estimate of the situation in the whole country. But we are assuming that this sampling is random. So it represents the whole country well. However, even if you do this, as you can understand, the number of households are limited. So if you do this experiment, and not the experiment, but sampling, again, with different households, as it's a random process, you'll end up with a different sample and a different average. Now you can get something like an 11. If you repeat this sampling again and again with the same number of households, with different random groups, you end up with different averages for each sample group. So, as you can see, this average for each group is also a random variable. It's also probably has a distribution. Okay, so we have two distributions here. You have to understand that the distribution 1 is the distribution of the quantity you're interested in. Here, the number of glassware, things made of glass, the number of such things in a house. This is the quantity you're interested in. The distribution of this, which means each household has different number of glassware, and what's the distribution of this in a country? That's one distribution. And the second distribution is the distribution of averages of your sample populations. If you repeat this many times, you will end up with many average numbers, and these average numbers also have a distribution. Okay, so I put these distributions side by side. The one on the left-hand side is the real distribution, the theoretical distribution, which this hypothetical person who's trying to find out, he or she doesn't know this distribution. We know that. It exists, and it's shown here. It's an average of 10. And on the right-hand side, this is a distribution of the averages, the numbers you get from the samples. However, the number of samples are limited. You do not sample the whole population. As you can see, it also has a distribution. So in some cases, you find your average to be 8.5. In some cases, you find it to be larger than 11. But in most of the cases, you find it to be something like 10. Here you have to understand that we did binning for this, because it's not an integer number, these averages. So you have to bin them. Put averages between, say, 9.25 and 9.75 into the bin called 9.50 here, 9.50. You can arrange these bins, the range of these bins as much as you want. However, this is what we did here. So we bin the numbers we obtained from those samples into bins, and we count the number of samples with an average in this range, which falls into that bin. This distribution on the right-hand side shows that data. Okay, so as you can see, as the number of samples are limited, so the distribution is a little bit noisy, or it shows some randomness. It's not as symmetrical and good looking or smooth looking as the one on the left hand side, which is the theoretical average. The number of samples there is in millions. However, we sampled a few hundred cases on the right hand side. So what if we increase the number of samples? So instead of taking 50 samples, 13 individuals in it, individual whole households in it, if we do it with hundreds of households, then the distribution will begin to look more smooth and more symmetrical. And if we increase this number to millions of samples, then we'll find out that the distribution of the averages of these 13 sample populations will begin to look like a bell-shaped curve, as shown on the bottom. This is called the normal distribution, the Gaussian distribution. So if you take samples out of a population and look at the distribution of the averages, the distribution of these averages is normal. And it's not it's not because the original distribution has a bell shape. This is the case for all types of distribution. For example, here you see on the top graph a distribution called exponential. As you can see, the distribution is not anything like a normal distribution. On the bottom graph, you see a distribution which is called homogeneous, which means that the frequency of all bins is equal. Even if these two distributions are completely different than a normal distribution, however, if you take samples out of these distributions and find the averages for those samples, as we did for the glassware stuff, some examples are shown with the red lines. Those are the averages of random samples taken out of the shown distributions. You'll find out that though the distribution of those averages is again give you a Gaussian normal distribution, bell-shaped distribution. A small reminder here, bell shape is not a good description because different types of distributions may have a bell shape. So what we're talking about here is a very specific distribution, which is called a normal distribution or Gaussian distribution. The name comes from the mathematician who described Gauss, who described this distribution. It looks like a bell. This distribution very often called bell-shaped distribution. However, a bell-shaped distribution is not a precise description. So we have to say that the averages, the distribution of the averages of the samples coming from any distribution is distributed normally or has a normal distribution or Gaussian distribution. This is called the central limit theorem. Because if you take more and more samples from a population, any population, as shown here, shape of the distribution, original distribution, is not important. If you take many samples out of any distribution and look at the distribution of the averages of these samples, it's always has the form of a Gaussian distribution. This is called the central limit theorem. Gaussian distribution is given here. Its formula is a little bit daunting, but it gives you this bell-shaped curve. And here the fx is the frequency of the bin x. For example, the number of households with 10 glassware. It's the frequency of it. You have to know the two parameters of the distribution, or in other words, two parameters describes the whole Gaussian distribution. Those parameters are the average, shown with mu here, and the standard deviation, which is shown with sigma here. Standard deviation, the average, you know. The standard deviation is a measure of the spread of the distribution. How wide or narrow is the distribution? Okay. If you know these two parameters, you can describe the whole distribution. So you can find out the frequency for each bin. That's the most important thing we have to know. We should know about the Gaussian distribution. Two parameters describe the whole Gaussian distribution. Again, this is not the bar graphs do not show you the real distribution of the averages, but here we show you the distribution we obtained from limited number of samples. If we did more and more samples, we will end up with a very smooth looking Gaussian distribution. But we kept the samples, the number of samples, to a certain limit. So we have a more noisy looking distribution. The theoretical one is shown with the light blue line. Okay, it doesn't matter which way you calculate the distribution. Either you use the formula, so find the real distribution, or do samples and find an approximate distribution. It doesn't matter. What it tells you that the likelihood of finding an average from a sample taken from a certain distribution, what's the likelihood of finding that average? For example, it tells you that finding a 9.5 average from any sample you take from this distribution is less than half of finding an average of 10. Of course, you have to understand that not exactly 10, but within the range of that bin. So this distribution tells you that the probability of finding a certain average when you take a sample. Okay, what's the use of this for us? So the important thing is the distribution of this averages is not dependent on the shape of the original distribution, but only the average value and the standard deviation of the original distribution. Okay? Any distribution has an average, and any distribution has a standard deviation. The distribution does not have to be Gaussian or normal to have these two values, but the shape of the distribution can be quite different, divergent. It doesn't matter. As long as you know these two parameters for the distribution, you know the distribution of the average values. So this is an interesting and powerful theorem, but what use does it have? Okay, so I'm not going to tell you about the real statistical methods here, but the idea is to give you an impression or a feeling for what statistical comparison does. Okay. So the essence of statistical comparison, I'm trying to illustrate here, this is not a real statistical guide for comparing groups. What we usually want to do is to find out that to compare two samples, and find that the average of these two groups, two sample groups, is different from each other, one from the other. Of course, you can look at the averages. For example, here you have a group of a sample group, which comes from a control group, and a group of samples coming from a treatment group. Okay, and the averages are different. However, we know that it doesn't mean that the control group and the treatment group are two different separate populations, coming from two separate populations. As we know from a previous example, even if you take the samples from the same population, because of random occurrences or chance, you end up with different averages for different samples. You don't have to find the same average for each sample you take from the same population. So this difference here between the control group and treatment group can be due to random chance. What we want to know is what's the probability of this. Okay? And when we say that statistical comparison, what we are trying to find out that if this difference between these averages is due to chance or not, due to a real difference between these two groups or due to chance. So there are two possibilities. One is that the drug has no effect, so the population, these two populations, the ones who did not get the drug and the ones who get the drug, actually represent the same population in terms of the parameter you're trying to measure. Here, the monocyte ratio, the ratio of the monocytes in the in general white blood cells. Okay, so you take a sample from a control group which did not take the drug, and you take the blood samples from a group which treated with the drug, and of course each person will have a different monocyte ratio, and you look at the distribution of that, and you find out the one on the as shown with the blue bars on the left hand side. You get the same distribution. These are the real distributions. These are not practically sampled distributions, but the real distribution, the distribution which we do not have access to. Okay? But the situation is like this. Those two distributions are the same. Drug has no effect means that the drug has effect, is effective, means that the group, the people who did not receive the treatment has one distribution shown with the blue bars, and the group which received the drug has a different distribution shown with the red ones, and they have two different averages. Okay, so we are trying to figure out which is the case in reality. So this difference, does it represent the case on the left hand side and the difference is due to just random occurrences, or is it due to the situation on the right hand side? Okay, we're trying to understand what the situation is, which one is correct. Okay, so let's assume that the drug has no effect, which means that if you know the population, these two parameters of the population, real population, the mu and the sigma, then you can easily deduce the probability of getting a certain average from a sample. Okay? Due to the central limit theorem. You don't have to know the distribution of the parameter you're trying to figure out. What you need is this the average and the standard deviation. If you know these, then you know the probability of getting a certain number, a certain average from a sample out of this population. What we get is from the treatment group is that 9.1 approximately. So we can calculate the probability of getting such a number if these two populations are the same. I mean, they both, the control group and the treatment group, come from the same population. Then, and the population has the average and standard deviation as shown on the left hand side. Then what's the probability of getting 9.1 as a sample? So we can see that the probability is this, as shown with the red arrow. This is some probability. If we got something like 8 or 8 something, then the probability will be even lower. However, it doesn't mean that getting such a number from a population with the average of 10 is impossible. It only tells you that there is a certain probability of getting it. Of course, for different averages, the probability can get very low. However, it doesn't drop to zero. So what statistical inference tells us that what is the probability of getting these two averages if they come from the same sample. If this probability is low, we say that it's not probable to get these two numbers by taking samples from the same population. So it's improbable, this difference is significant, which means that improbable. If it's the value of probability is high, then we say that yes, it's probable that these two samples come from the same population, so this difference is insignificant. Of course, this is an arbitrary decision, as you can understand. Where do you put the threshold? What is a probability where you put the border between significant and insignificant results is a little bit tricky. Again, this is not what really happens because we do not know the real distribution of the control group. What we are trying to figure out that what's the probability of getting these two averages from the same population. We do not know what the population really is. The control population is. Here, in this example, we know what the control population is. However, the logic is the same. So what we are trying to figure out that what's the probability of getting these two different results from the same population. And that probability gives you how likely it is to get these differences in the averages by random chance. And if it's not that likely, you decide that it's due to the difference between the populations. And if it's more likely, then you decide that it's just random chance. However, this is the only information you have. What's the probability of this happening? It's really not clear-cut definition. So you have to understand this logic behind the statistical inference, statistical decision making. Okay. Here we talked about the difference between averages between two sample groups. You can extend this discussion for the other parameter, the standard deviation, and you can also try to figure out if the standard deviation between two groups are different or not, and so on and so forth. But the logic behind it is the same. However, we did not talk about the techniques to do that, the mathematical techniques to do that. So, see you in the next lecture.